Okay. In this video, we want to solve first problem. We want to learn how to approach a problem because the idea that we want to use for this problem is so much famous and useful also in other IMO problems, in USAMO problems, and also for BMO problems, British Mathematical Olympiad. So we first approach this problem and learn how to solve these types of problems. Then at the end, I will leave some homeworks with related ideas from prestigious national exams and other IMO problems. Okay, problem one. The Bank of Oslo issues two types of coin. Aluminium denoted A and bronze denoted B. Marion has N aluminium coins and N bronze coins arranged in a row in some arbitrary initial order. A chain is any subsequence of consecutive coins of the same type. So here it is definition of chain, and we have NA, NB, given a fixed positive integer k less than or equal to n. Marian repeatedly performs the following operation. She identifies the longest chain containing the kth coin from the left and move all coins in that chain to the left end of the row. Okay, so let's see. It says, for example, if n4 k4, the process is starting from the ordering AABBB, ABA would be this. Okay, let's analyze this one. K is 4, N is 4 means 4 A's, 4 B's. So we have 8 A's and B's. Okay. If K is 4, we should consider 1, 2, 3, 4. Then it's okay, we consider the chain. The chain was what? Subsequence of consecutive coins of the same type. So this chain. And then it says what? It says she identifies the longest chain containing the kth coin from the left. So from the left, if you consider fourth coin, because k is 4, it will be this, and the longest chain containing fourth coin will be this. Now we should do what? It says, and moves all coins in that chain to the left end of the row. So we move this board here. So it will be 3 B's, 2 A's, 1 A here, BA. So let me explain. A, B, 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 A, B, A. So fourth coin, longest chain containing that. Now let's move it here. So we move 3 B's here. What are the things that are left? 2A, 1A here, BA. Now again, if you consider fourth coin from left, it will be this. Longest chain containing fourth coin is this. Now moving this to left, it will be what? Look, this one is exactly this one. Now let's do it again. 3 A's. Now we have 3 B's and BA here. So it will be what? It will be this. In next step, we consider fourth coin. We move it to the left. Which we move what to the left? The chain, longest chain containing this one. Now, if we move it again to left, it will be 1, 2, 3, 4 B's and 3 A's and 1 A, 4 A's. If we do it again, if it comes to fourth one, longest chain containing this, moving this to the left, so it won't change. So after this, again, we have same thing. 4 B's, 4 A's. Okay. Let's see the problem wants what? Find all pairs nk with k greater than equal 1 to n, because we have 2n A's and B's, such that n A's and B's, such that for every initial ordering, at some moment during the process, the leftmost n coins will all be of the same type. So like this, for example, we have 4 B's, 4 A's. It says find all n and k that for every initial ordering, we will reach this case. Okay. For solving this problem, I can say the most useful idea and the most useful approach is to consider small example. Like what? Here it says n, it doesn't say anything for n, for example, at least what. So let's consider n1, and we know k is at most 1 and 2n. So If n is 1, it means that we have 1a, 1b, and k is from 1 to 2n, which is 2. So because we have n1, we have n-a's, n-b's, we have 1a, 1b, ab, or ba. And as you can see, the initial case is okay. So we conclude that n1, k1 is okay, n1, k2 also is okay. Now, look, let me tell you initial case works like what. So for some n's, it is obvious, for example, for 1, 2, 2. For example, a number, for example, 5 is easy. Then 5 is a little harder, and 6. Here in this part, you can find the idea. For example, if you want to check for 20, it is hard. If you check for 1, it is obvious and you can't find anything. But this frontier, this bound is exactly the right place that you can find the idea. Okay, let's consider the next one. N equal to 2. K can be from 1 to 4. We have 4, 2a's, 2b's. Let's consider first K1. If we have A, and if we have B, for example, AB. If we consider always first coin, so if we move it to left again, it will be again AB, AB. So we conclude that N, K, N2, K1 doesn't work. Now I think we can generalize it for any N and for K1. That is bad. Let's check. For any N, let me write it in other page. For all N at least 2. If K is 1, you can consider this part A, B, and then N minus A, A's, and N minus 1, N minus 1 A's, N minus 1 B's. So if you consider always first one, the longest chain containing that will be itself, and it won't change. So we proved an ahan. When you reach anything that maybe is important, and here it's obviously important, we write it as a lemma. In lemma 1, we proved for all n such that n is greater than equal to k equal 1 is bad. Means we can't reach. Bad and good, bad means we can't reach the case that all first n coins are same. Is lemma 1 and for a problem when you want to approach that, when you want to solve it, maybe you reach 10 lemmas and we don't know which of them is useful, which of them not. At the end, for example, you use 7 lemmas from 10 lemmas that you've reached. Okay, so it is not important. This lemma, for example, a lemma is useful or not. You write all things that maybe can be useful. Okay, at the end we will understand. So K1 doesn't work. K2. Let's see, can we find a counter example for that? K2, it will be, for example, A. We have two A's. Look, uh, at the end we want to reach what? If it is good, AABB or BBAA. Let's consider the cases that are not like this. It will be AB, AB. Similarly, we can say BABA is same, ABBA. Okay, so we should only consider these two cases. Now, if case 2, if we consider this one, in next step it will be B. We move it to left, BAAB. And if we select this one again, the longest chain containing that will be this, we will reach AABB. And this one again, if you consider second one, you should consider this one. So it will be, we've considered here, BBAA. So K2 is good. N2, K2 is good. Let's consider K3. If we consider again ABAB, we have two types of coins, and ABBA. So if we consider second one, it will be BAAB. If we consider second one again here, it will be AABB. Sorry. We should consider third one, not second one. Because K is 3. It will be AABB, okay. And if we consider this one, we should move this one to left. So it will be BBAA. Okay, so K3 we will see it's good. If we consider K4, for K4, if you have AB, if we move this one, it will be what? It will be BABA. Again, if we move this one, it goes to this one again. Okay, so we will understand N2, K4 is 3 was good. We've reached, it is bad. So let's write the things we reached for N1, all of them good. For N2, K1 and K4 is bad. So for NK, N1, K1, N1, K2, all of them good. For N2, K1 is bad. For N2, K2 is good. For N2, K3 is good. For N2, K4 is bad. Okay. Now let's consider this case. We have AB, AB. Now I want to find a pattern like this. Like what? To find many bad cases. I say, for example, if you have two A's, two B's, two A's, two B's. So it will be like what? If you consider, for example, this term or this term, last two terms. For example, it is N what? N8. And K, for example, 8 or K7. Then we move these two B's to left. Then it will be AA, BB, AA. And again, if it's like this or this, we go to this. Okay? So we will understand N8 if N is sorry, N is not 8, N is 4. 2N is 8 because N was number of 8, not length of our string. For let me correct this part. And 4, K8 and K7 bad. Now let me tell you something. Is it important that the length of all of them be equal or not? We don't know. Let's just check something. Do you agree also here if we consider first one and second one it's bad? Means 4, 4, 1, 2. Oh, because when you select 1, 2, it doesn't change. Why? Because we have, for example, AA for this initial case, BB, AA, BB. Then if it considers, for example, first one or second one, we will see, okay, it goes to itself again because we consider this chain and move it to left again. So by this condition, by these things, we can find many N and Ks that are bad. Let's check some of them. Instead of two A's, if you consider some A's, if you consider NA and B, we want to find bad things. It is not good because the initial case is good. But if instead of N A's, we consider N minus 1 A's, okay? And for example, N minus 1 B's and 1A, 1B, okay? Or you can say, for example, N B's and 1A. Now in this case, if K is 1, 2 to N minus 1, it goes to itself. Okay, so we've considered that if K is from 1 to N minus 1, it is bad. So lemma 2, we found many K's that are bad. For all N, if K is from, for all N, if K is from 1 to N minus 1, it is bad, like the previous case, it is bad. Now here we've generalized this part. For 1, for example, for 2 are bad. What about this case? So it was for N4. Let's consider, for example, an N that is larger, for example, N8. Okay, and we want to see for which of them it is bad. Suppose, for example, N8. If we consider, we have 8 A's, 8 B's. If we consider 4 A's, 4 B's, 4 A's, 4 B's, it will be bad. Okay? Which K's are bad? This K, this K, this K, this K. Because then it goes to what? It goes to BB, BB, A, 4 B's, and 4 A's. So if N is 8 for K, 16, 15, 14, 16, 15, 14, 13, it will be bad. And as you can see, the N's that we are considering is multiple of 8. Okay? Now let's consider, for example, maybe N is 9. See, we can consider which numbers are bad. If we have N9, for example, we can say, okay, we have 9, 4 A's, 4 B's, then, for example, 5 A's, 1, 2, 3, 4, 5, 5 B's. Okay, because look, for example, when we change it to, if it is this, when we apply it once, it will be what? 1, 2, 3, 5 B's, then 4 A's, then 4 B's, and 1, 2, 3, 4, 5 B's. Let's check 4 A's, 4 B's, and 5 A's. 1, 2, 3, 4, 5. And we go to this one, the next part. This 5 A's goes here, 1, 2, 3, 4, 5 A's. Then 5 B's, 1, 2, 3, 4, 5. Then 4 A's, 1, 2, 3, 4. 4 and 4 B's, okay? So if you select this one, here is good, but this part also good, but this part it calls to reach another case. But if we can check that for this one it will be bad, but if we check for example this it will be good. So also for N4, which case are good? The last one 18 and 17, 16, 14. 18, 17, 16, 14, 15. Okay, 15, 16, 17, 18. These four Ks are bad. Now let's generalize it. For any n, which large Ks are bad? For example, k equal to 2n is bad. This form help us. Let's generalize this form. We consider each of them. The longest chain we consider is a block. Okay, so here we have 4 blocks. So the idea for proving which Ks are bad to consider 4 blocks. Okay, let's generalize it for any n. Suppose we have blocks, some A's, 4 blocks, some B's, some A's, some B's. Okay, now suppose we have, for example, we want to select K. K should be at most here, at least. It is Kth one, it is 2n, and suppose the length here is T. And we know that each of the length here should be at least T, like the previous example. Then, and we can say it is A, it is B, it is A, it is B. If all of them at least T and kth one is exactly here, we make sure that always we have this form ABAB or BABA. The blocks won't merge. Now in next step, let's see it is what? T is what? T is last one minus first one, 2n minus k plus 1. And 2n is at least what? 2n is at least 4t. T was what? Was 4, 2n minus k plus 1. So it will be what? If we expand this, it will be 8n minus 4k plus 4. Now we want to find k, so we take negative 4k to the left hand side, 4k greater than equal, take 2n to right hand side, 8n minus 2n is 6n plus 4. Now we divide both sides by 4 to see k is at least what? K is at least 6n plus 4 over 4. which will be what? 6n over 4 plus 4 over 4. 6n over 4 is what? 3n over 2 plus 1. So, as lemma 3, we've reached another good lemma. Lemma 3. For all n, if k is greater than equal 3n over 2 plus 1, and we know k is at most 2n, okay, by assumption of the problem. So we can also write it also without writing this, it will be okay. It is this k is bad. The k that is in this interval is bad because of this proof. Okay, so let's see which k's are left. K less than this, because for large k we proved, also for small k's we proved 1 to n minus 1. So the k's that are left, let's check, are from n that we could consider up to less than this part, because it is greater than equal this. So less than, strictly less than 3n over 2 plus 1. Okay, because it is strictly less than, and we know that, so we can say what? I want to change it to something less than or equal that. So here, when, for example, this is important, when we have m and n, for example, are integers in general. When m is strictly less than n, it is equivalent, you can say m is at most n plus 1. When m is less than n over 2 strictly, you can say m is at most n over 2, because the units will be 1 over 2, 1 over 2, minus 1 over 2. Okay. For example, when it is n over 3, you can use similar ways. So here, we should consider the case that k is at least this and at most 3n over 2 plus 1 minus 1 over 2. So it will be what? It will be 3n over 2 plus 1 over 2. So for k's between these two numbers, n and 3n over 2 plus 1, we should check them, that is it good or bad. Now, we've considered blocks, okay? Here we understood, okay, the number of blocks are decreasing. And the problem says what? It is, for example, n and k is good if the number of blocks equal to what? When it says the first n coins should be same. All a's, for example, all b's, or vice versa, b's, a's. So we define a function, number of, so any longest chain, we consider in each part longest chain, and we consider them blocks. So f is number of blocks, and in this case n is 2. F is 2. We want to see, can we reach to f2 or not? Suppose if, for example, f equal to 3, okay? If f equal to 3, and we have, for example, some a's, some b's, and some a's. So how many b's are there here? N, because number of b's equal to a. For example, here, if we have I a's, here we have n minus. Now in this case, if you select these parts, it will be good for this case, because it won't change. But if the k we have has what property? If the k that we have is, for example, here, 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 in all these ports, then when you move it, f will be 2, because these two a's will merge. What about this one? Also, if you select this port, you will see what? You will see all of them. The two a's will be merged together, and again f will be 2. So we understand, if f equal to 3, eventually it changed to f2. Why? Because we are considering k at least n. We know I is strictly less than n. So k's will be here in some part here after n to 3n over 2 plus 1. So for this case, if f equal to 3, f changes to 2, and that n and k are good. Now let's consider f4. We want to see, can we decrease it? Will f decrease eventually or not? So let's consider again k less than or equal what? 3n over 2 plus 1 over 2. So Here, suppose, for example, F is something. We have some blocks. I want to prove in each step F will be decreased to reach to always. So let's see, is it correct or not? Suppose we have something like this. We have this, this. So somehow we can say we are using induction on K, on F. F2 we proved, also F3 we proved that they changed to F2. Suppose, for example, we've considered for F2 to m minus 1 and we want to prove for F. Here, for example, without loss of generality, it is B, A, B, and again, without loss of generality, also we have some other blocks in general. We have these. So, again, without loss of generality, suppose, for example, it is B, A, B. It is not important. So, and I want to say in next step, if case 1, you can consider BAB and also ABA. Both of them will be same the proof. And I will tell you why. Suppose case 1 is here. Then do you agree we should move what? We should move this to left side. If it was A, this A and this A, these two blocks will be merged, but if it is B, it's okay. It won't be increased, okay? But these two A's will merge and F will be decreased, okay? So if case 1 is select, if case 1 selects a block that on both sides we have, for example, if it is B, we have A's. So F will be decreased in this case. So we should consider only which part. So we should consider, and if F decrease, then what happens? We can use induction and say, okay, we can reach F equal to 2. So the only case we should check is if case 1 select the last block. So if it is A, for example, it is B, and so on. So if it is A, if you select, for example, this one, again, F will be decreased. So we should only consider B. And suppose case 1 is here. So when case 1 is here and you don't want that F decrease, it means what? This piece goes to here, for example, it is A. The number of blocks at first will be what? 1, 2, because AB, the last one is AB, is 2T. The number of blocks should be even. And 2T is at least 4. And if we want a case that F won't be decreased, it is what? For example, when we select here this part, okay, when we select this part, it goes here, then next parts also should be, for example, if this A is so much small and it goes here, then case 1 doesn't select last one. So all of them should have length that reach K. So when it is K, so we need this length from K to 2n for all of them. This length is what? 2n minus K plus 1. So the length of all of them should be at least 2n minus K plus 1. How many blocks are there? At least 4. So 2n will be at least 4 times 2n minus K plus 1. It will be what? 8n minus 4k plus 4. And if we take 2n to right hand side, 6n, 8n minus 2n, these to left hand side, it will be exactly the inequality we worked on that before, plus 4. Then if you divide by 4k is greater than or equal to 6n over 4, which is 3n over 2, plus 1. But we know k is at most what? 3n over 2 plus 1. So k is at most 3n over 2 plus 1 over 2. So we conclude that 3n over 2 plus 1 over 2 is at least 3n over 2 plus 1. We cancel this and we prove 1 over 2 is at least 1. So it is contradiction. So here we proved that for this case, all, let me tell you, all initial cases are good because You can reach from in that initial case to the case that f is 2 means all n, all first n coins are same, and the problem wanted that. Why? Because here it says at some moment during the process the leftmost n coins will all be of the same type, so f is 2. Now let's consider, in this problem we've considered two things. The defining a function f, we call it invariant. Okay, we call invariant, and using a small cases. This idea is so much useful. Let me tell you first an IMO problem from IMO 2019, problem number 5. Okay, you can solve this problem, but part B related to recursive sequence. But part A, only focus on part A. Part A exactly using small cases and invariants. And the idea is exactly same. Okay, so background ideas are so much useful, and we work on two of. There are around 40, 50 important background ideas in each topic: combinatoric geometry, algebra, and number theory. If you want to learn them, as I said before, feel free to send message to my WhatsApp number in the description and comments. Okay, it was homework number 1. Let me tell you another homeworks. Okay, the next one, homework number 2. It is for BMO Round 2 national level, British Mathematical Olympiad, and it's for 2023. We have 4 problems. It is problem number 3. Again, you can use same idea to solve this. Let me write homework 3. This one is homework 3. Again, British Mathematical Olympiad Round 2 2023. Second problem, again, combination of, for example, something you want to say impossible, considering small examples. Invariant, it's homework number 3. Homework number 4, it is PMO problem, national level. It's for Philippine Mathematical Olympiad 2023, national stage. You can solve exactly with same idea. Again, as you can see, we have again string, for example, in terms of A and G. In IMO problem, we had A and B here, A and G, and you should prove something will eventually be stopped. Okay. Homework 4. Let me write 2 more problems, one of them from USAMO, homework 5, USAMO 2023. This problem also related a little to number theory, but except that, you should consider again small example, find the idea, something possible, something impossible, impossible with invariant, possible with finding examples, like exactly the problem we worked on. And homework number 6, I can tell you another problem related to considering small example, because there are lots of problems, but I think these 5 homeworks enough, because next one is considering a small example and also apply graphs. Some ideas in graphs, because we've not worked on that yet. So I think these 5 homeworks enough. You can work on them if you wanted hints or uh, at first I say it's important to try as much as you can, but if you wanted hint, as I said before, feel free to send message to my WhatsApp number in the description and comments. Okay, we will work on new problems, new IMO problems, USAMO problems, BMO problems, and for each problem we work on the background idea, and after that I will leave some homeworks for you. Okay, thanks for watching this video. Have a good day. Bye.